So this is a big one. This is what we've been building up to all year, the fundamental theorem of calculus. So we're going to there's actually two parts to the fundamental theorem of calculus. So they're called part one and part two. And today we're going to just talk about part one. So we can abbreviate it just as FTC I. All right. Before we get to FTC I, I'm going to give you some definitions. This is something we have already talked about. You don't have to write all these words down, but what I will have you write down is this definition here, which is what an integral is. We already talked about it last time, but an integral represents when we take a Riemann sum and we let the number of rectangles or subintervals that we're using approach infinity. So now we have an infinite sum that we're trying to add up, and Leibniz decided, okay, well, instead of using sigma notation to indicate that it's now an infinite sum, let's use this new thing. I'll call it an integral. And that integral will look like an elongated S for sum. And then on the ends of the integral, I'll put where the endpoints of the interval that I'm looking for the area underneath are. And then since when I use more and more subintervals, they get closer and closer together, right? The endpoints of each subinterval get closer and closer together. Our delta x gets smaller and smaller. So xi goes from being a finite index to just all the endpoints become the continuous number line x, which is why xi just becomes the variable x. And then delta x, which actually represents a finite width, becomes infinitely thin, and we replace it with this dx, right? All that means is that this limit would be the same no matter if you use right endpoints, if you use left endpoints, if you use midpoints, or any other point on the subintervals to get the height of each one. As long as you're taking the limit as n approaches infinity, it doesn't matter what value of x you actually use to get your height on your subintervals. All right. So that's just integral notation. And as I said, we can interpret the integral as the area under the curve y equals f of x from a to b. But one thing I want to point out is that if the curve goes below the x-axis, if you think of a rectangle below the x-axis, that rectangle is going to have a negative height, right? Like say this could be like -2. Well, when you multiply that -2 by your positive delta x will always be positive, you end up with a negative area. So the integral actually represents what we call the net area. It's the difference of areas. So the areas above the x-axis will be positive, the areas below will be negative, and then the overall integral from a to b will be the net area. So positive area, take out the negative area. Does that make sense? Any questions about that? So with that in mind, before we get to the fundamental theorem, we're going to define just some basic intuitive properties of integrals, just based on this concept of it's the net area under a curve on an interval. Oh, no, we're not. First thing we're going to do is an example where we convert from limit sigma notation into integral notation. So here I'm given the limit as n approaches infinity of sigma from I equals 1 to n of x sub I cubed plus xi sine I delta x. We did one where we went from integral to the limit notation. Now we're going to go the other direction from the sigma limit notation, rewrite it as an integral. This is actually the more straightforward one. All right, what does this limit and sigma become? Yeah, the swoopy thing, the integral sign, right? That just becomes the integral. On the integral go my endpoints. What are my endpoints? What's my interval in this case? 0 to pi, right here. 0 to pi. All the x's that were indexed just become the variable x. So this is just going to be x cubed plus x sine x. And what does delta x become? It gets infinitely thin, so we rename it from delta x to what? Just dx, the differential dx. And that's it. Not that painful. All right. Couple properties of the integral. An integral of a constant from a to b is just equal to that constant times b minus a. Just remember that if we interpret an integral as an area, the graph of a constant is what? What does the graph of y equals a constant look like? Like y equals 4. Yeah, I mean, it's going to be a horizontal line, right? And Dylan's exactly right. It's going to be a rectangle because I'm only looking at that line on an interval between a and b. And so if I'm looking for the area under that rectangle between a and b, isn't that just base times height? The base would be b minus a. The height is whatever your constant is. In this case, it's 4. So it'd just be 4 times b minus a. So in general, the integral of any constant is just that constant times b minus a. All right, some other ones that are kind of intuitive. The integral of a sum of two functions is equal to the integral of the first plus the integral of the second. If you have an integral of a constant times a function, you are allowed to factor that constant out of the integral. So it equals c times the integral of that function. These are pretty similar to rules for derivatives, right? And then fourth is also the integral of a difference of two functions is equal to the integral of the first minus the integral of the second. This fifth one, I want to give you some intuition for. This says if you have an integral of f from a to c, and then you add the integral of the same function from c to b, then you can kind of cut out the middleman. You can cut out that c and just integrate the function from a to b. And the reason is, so if I put them in this order, it'll be pretty intuitive. So I have a, c, b. So if I do the integral from a to c, that's this area. And then if I add the integral from c to b, that's this area. Well, isn't what I'm finding just really the integral, the total area from a to b, all of that? So you can condense it into a single integral, okay? Oh, in here, so this goes from a to c. The first one goes from a to c, and the second one goes from c to b. For the second one, yes, this is c, and then on top is b. The upper integral is b. Let me just make sure where we're at here. I know how I want to talk about this. Okay, we're getting there. So we're going to talk about kind of a new kind of function. I'm going to call it g of x. So g is a function of what variable? Don't look at the right-hand side, just look at the left. G is a function of what variable? X, okay? But notice that x is the upper limit of this integral, right? T is what we call a dummy variable. It doesn't really matter. But g is a function of x. So what happens, the way you can think of it, pretend x is a value on the x-axis that falls between a and b. As I increase x from a to b, this area is going to accumulate, right? So as I increase x from a to b, that area accumulates. So g is something we refer to as an accumulation function. As we increase x from a to b, the area will begin to more and more accumulate. So we're going to do a little bit of work with an accumulation function. I am going to have you sketch this one out as best you can. It's nothing too crazy, but it looks like this. Yeah, sorry about that. We good? Okay. All right, so here I've defined g of x to be the function that is defined as the integral from 0 to x of f of t dt. So it's the area under that curve starting at 0 up to whatever x value I input. Remember that area above the x-axis is positive, below the x-axis that's negative. So right now we're just going to basically use geometry to find certain values of g. I want g of 0, 1, 2, 3, 4, and 5. So we'll start with g of 0. So thinking about this, g of 0 is the integral from 0 to 0. So I'm replacing my x with the input, which is 0 in this case, of f of t dt. Well, that would just be the area under a single point. Does a single point have any width? No, a single point is dimensionless, right? So how much area is there under a single point? 0. And that's going to be true for any time that your upper and lower limits are the same. The integral will evaluate to 0. Okay? All right, so if we just think of this in terms of a coordinate that we got for g, we input 0, we got an output of 0. So that corresponds to the point 0, 0, right? All right, let's look at g of 1. That's the integral from 0 to 1 of f of t dt. So that's the area under the curve between 0 and 1. Here's 0, here's 1. All right, AP Calculus, what shape is that? Do we know how to find the area of a triangle? How? What's the base of that triangle? What's the height of that triangle? What's the area? 1 times 2 divided by 2 would be 1, right? Good. So my output is 1. Great. So that corresponds to the point 1, 1, right? My input was 1, my output was 1. Let's keep going. G of 2 is the integral from 0 to 2 of f of t dt. So it's all the area under the curve between 0 and 2, right? Well, we already found out that that area is 1, but now I need to go all the way to 2. What shape am I adding on here? What's the area of that rectangle? 2. So what's the total area between 0 and 2 under the curve? It'd be the triangle plus the rectangle, so it'd be 3, right? Great. So my output is 3. That's going to correspond to the point 2, 3. My input was 2. My output was 3. This one we're going to kind of have to estimate. So g of 3. Now we have the integral from 0 to 3 of f of t dt. So I'm going to add on this much area. Now, we don't have a geometric formula for finding that. We're just going to estimate it. How much area, additional area, do you think that is? More than a full square, right? More than 1? What do you want to go with? Not more than 2. Do you think it's 1.5? That's good enough for me. Let's just do, it's roughly 1.5. You guys okay with that? So if I add on an additional 1.5 to that, what's my output going to be? 4.5, right? So I'd have the point 3 comma 4.5. All right, but now g of 4 would be the integral from 0 to 4. So it'd be all that area plus this. But we change our interpretation because now we're below the x-axis. So that area is considered negative. So what's my output going to be for g of 4? Why? Good. This negative area is going to cancel out this positive area, right? Which is basically just going to leave me with this, which was 3. Does that make sense? I agree with Dylan, 3. So g of 4 is 3. That gives me the point 4, 3. All right, one more to do. G of 5. Integral 0 to 5. We got a little more negative area. What do you think? Yeah, I would agree, because this is symmetric, so if we're calling that 1.5, we're going to take off an additional 1.5. 3 minus 1.5 is 1.5. All right, so that's the coordinate 5 comma 1.5. So now if I wanted to, I could get a rough idea about what the function g looks like graphically, because I have 5 coordinates that I know fall on the function g, right? I have 0, 0, 1, 1, 2, 3, 3, 4.5, 4, 3, and 5, 1.5. So if I tried to graph g, I'll graph it over f. Let's see what it would look like. So I'll do it in red. So we'd have 0, 0, we'd have 1, 1, we'd have 2, 3, 3, 4.5. It's going to be like way up here. 4, 3, 5, 1.5. So probably something like this. Right? Look at the relationship between g and f. Here, f is crossing the x-axis from going from positive y values to negative y values, right? What's going on with g does it look like at that point? What do we call this? A max? Right? Here I have all positive, these are all positive y values for f, right? What's g doing on that interval? What is it doing? It's increasing. Here we have all negative y values of f. What's g doing on that interval? Decreasing? Anybody want to guess at what you think the relationship between f and g is?
F is the derivative of g.
F is the derivative of g. Maybe. F is the derivative of g. That makes g, I'm going to use some new language, the antiderivative of f, yeah? The opposite of that. If f is the derivative of g, g is the antiderivative of f, which makes me suspicious that if g is the antiderivative of f, that maybe integration, which is what we're doing to f here, is just anti-differentiation, the opposite of differentiation. All right, well, let's see. Here's what I'm going to do. I'm going to start with this graph. We're going to develop the fundamental theorem of calculus here. I'm going to start with this graph. And in that graph, this is just an arbitrary graph between A and B. I drew a rectangle, okay? And then I shaded the area under the curve on that interval, right? And I'm going to use the rectangle to approximate the area of this shaded region. So it's not going to give me the exact area, but it'll be a decent approximation, right? Right now you can tell it's kind of going to be an overestimate because it overlaps it a little bit. Well, let's just talk about that area in terms of the rectangle itself. Well, the base of this rectangle is just the distance h, right? And the height of that rectangle is f of x. So I could say h times f of x, yeah? And that's approximately the area under the curve. Well, another way I could define that curve is I'm going to define an accumulation function. Let g of x equal the integral from a to x of f of t dt. So g of x is just the area from a to wherever I let x stop of f of t dt. So another way I could find that area is I could find g of b, I'm sorry, g of x plus h. All right, so g of x plus h, I would be replacing this x with the upper limit of x plus h, so it would be the area from a all the way over to x plus h, right? It would be all that area. And then I could subtract off g of x. So that would be taking away the area from a up to x. So I'd be taking this away. Yeah? And then that would leave me with just the area under the curve over that interval, x to x plus h. Does everybody agree with that? All right, those are only approximately equal each other because I'm using some finite distance h. The way I could get those two things to be the exact same is let h get smaller and smaller. The thinner and thinner that rectangle, the more closely the area inside the rectangle will approximate the area under the curve inside that rectangle, right? Well, if I want it to be exactly equal, I can let h approach 0, right? And what I'm going to do is divide h to the other side and do just that. If I let h go to 0, then they should be exactly equal, and I no longer need to use an approximate symbol. But what we've created here is something that should be relatively familiar. That's a very special kind of limit. What's another name for the limit as h approaches 0 of g of x plus h minus g of x over h? The derivative of g. This equals g prime. That's the definition of derivative, right? So what did we just show? We just showed that if g of x is equal to the integral from a to x of f of t, then g prime of x equals f of x. This is pretty important because now what we've established is that a derivative undoes an integral, meaning a derivative and integrals are inverse processes, like addition and subtraction, or like multiplication and division. These two things that come from completely different problems, right? Derivative comes from trying to find an instantaneous rate of change, and an integral comes from trying to find an area under a curve. Just so happen to be inverse processes, right? They undo each other. Pretty big idea in math is that concept of duality, right? A lot of things have inverses to them. Like I said, addition, subtraction, multiplication, division. Square something, you can take a square root of something. And now we know that integrals and derivatives are also inverses, and they undo each other. So the process of finding an integral is really the inverse of the process of finding a derivative. AKA, we refer to that process as finding the antiderivative. That's the fundamental theorem of calculus, part 1. I don't want you to get too in your head about it. All it does is establish that derivatives and integrals are inverse processes. Which is huge. Because what that means is, instead of trying to evaluate an integral by taking a limit of a sum as n approaches infinity, which can be pretty cumbersome, since we now know that it's just the inverse of a derivative, if we can kind of reverse engineer some of our differentiation formulas, we'll be able to use them to find integrals. All right. So I'm going to do, I think, 2 examples of the types of problems you're going to see from this particular section. This just says, find the derivative of the function g of x equals the integral from 0 to x of root 1 plus t squared dt. So we want to know what g prime is. Well, the fundamental theorem of calculus, there is some nuance, so I want you to pay attention. The t is a dummy variable. It will not show up in our derivative. Notice that it's the integral from a to x of f of t dt, but when we take the derivative, g prime is equal to f of x. Okay? That'll be a little bit more intuitive why that happens after our next lesson, which is fundamental theorem part 2. I'll come back and re-mention sort of why that happens. But all you have to know is that, remember that your g is a function of x. G is not a function of t. T is a dummy variable. So g prime equals f of x. Okay? All right. Well, our function in this case is just this, right? But instead of t, we're going to have x. So when we take the derivative basically undoes d dx of that integral. It undoes the integral. Those two things cancel each other out. So g prime is then root 1 plus, but not t, it's going to be x, just root 1 plus x squared. So when you take the derivative of an integral, they undo each other. Just like if I took some function, if I go, what's 3x squared, and I add 3 and then I subtract 3, what I'm left with is just the original function, right? All right. This can get a little bit more complex, though, when we're taking the derivative of a composite function. On the last one, our input, g of x, our input was just x, right? On this one, what's our input? X to the fourth. So if you think of this, instead of being g of x, this is actually more like g of x to the fourth. If I'm trying to take the derivative of g of x to the fourth, what rule am I going to have to use? What rule do we have to use when we have composite functions and we're trying to take the derivative of them? The chain rule. And that's what rule I have to use here. I have an outside function and I have an inside function. So an easier way to think about this might be to first generalize it. So let's do this. Let's call x to the fourth g of x. So really what I'm doing is taking the derivative of the integral from 0 to g of x of secant t dt. Well, chain rule says derivative of the outside function, leave the inside function plugged in, right? So when I do the derivative of this outside function, I'm dealing with the integral. So that would just eliminate the integral. But instead of secant t, I'm going to leave my inside function plugged in. What's my inside function in this case? Not x. G of x is the inner function, right? So I'm going to do secant of g of x, and then I multiply by the derivative of the inner function, right? To finish out the chain rule. So my answer here is going to be secant of g of x times the derivative of g of x. So now that we've done that, let's go back to actually viewing g of x as what it is, which is x to the fourth. So I have secant x to the fourth times the derivative of x to the fourth. What's the derivative of x to the fourth? 4x cubed, right? So this is 4x cubed times secant x to the fourth.
Hey, Mr. Toller.
Go ahead.
What happens to the dt?
The dt, the dt you can think of as part of the integral operator. Like this and this are all one operation, okay? And so when we take the derivative, it eliminates the integral altogether.
Okay.
And again, I think that you'll have a little bit more clarity on why this works this way once we go over the fundamental theorem of calculus part 2, and I'll kind of remind you of that. But for now, just the integral and the differential all make up the integral itself. That's the whole operation. So once you take the derivative, it eliminates the integral operation. Because we are taking the derivative, but the outermost function is the integral. So the derivative just eliminates the integral, right? Right. And then with chain rule, we only had to do the derivative of the inside function at the end, which is just the x to the fourth, right? It's going to take a minute. It's going to take a few problems for you guys to get comfortable with this. And again, you'll have more comfort, I think, once we go over part 2. But for now, just ask questions. You got about 15 minutes to get started on the problem set, so I'll be here to answer any questions. I did open up, I left the AP Classroom assignment open. We only had like 70% of people submit. Remember, these are now going in as assessment scores. So you do not want a 0 in there. Make sure that you are attempting those. I opened it up through Tuesday at midnight so that if you had questions on any of them, you would still have an office hours to come see me. But there's an additional one that I assigned. Hold on, let me make sure that's the case and I'm not thinking of statistics. Let's see.